Is that action?
Yes, you're all.
Yes, you're out of a job. All right.
Okay, no, I was confused.
Okay. Welcome to 702, either 10702 or 36702, depending on how you signed up. The website is on Aarthi's page. So it's cmu.edu, total Aarthi, class 10702 _spring 13. So Aarthi Singh over there is the co-instructor. We'll be taking turns here throughout the year. In principle, you're supposed to have taken 701, which just left the room, and 36705. If you don't have the prerequisites and want to take the course, that's okay, but then the responsibility is yours to make sure you make up any missing material. You'll find that we do rely on that material in the previous courses quite a bit. Okay? The 705 lecture notes are left up on my webpage, so if you want to download those and go through them yourself, you're welcome to. 701 material will probably be found. It's probably best if you did take both courses, but again, that's up to you. There's we didn't print out the syllabus because it's not quite complete, but also you'll be able to download it anyway from the website. I'll just tell you some of the highlights here, and then you can see the details when you download the syllabus. So first of all, of course, lectures are here Mondays and Wednesdays, 1:30. As you can see from the technology right there, we're experimenting with something new. We're going to tape the lectures. We'll see how it goes. If the tapes are good, we'll put them up. And so if you miss a lecture, you can look at them online, or if you feel like it was such a great lecture, you want to see it 2 or 3 times, you can go look at it. All right. And we have 2 TAs. Akshay was here earlier, right there. Efi is around, I think, right?
He's not here today.
Oh, that's right, he isn't back yet. So anyway, there's 2 TAs. We'll be posting everybody's office hours and tutorial times and so on will be posted on the website and on the syllabus very soon. Okay, some of that information is up there. It'll be completed very soon. So you definitely want to check the website. Michelle Martin in Gates 8001 is the course secretary, so she'll be in charge probably of collecting assignments, right, and things like that. Most of the notes are based on the ongoing book that I'm writing with John Lafferty in Honolulu, and we'll be posting the chapters on the Blackboard. So there's a Blackboard for this course. Everybody know what Blackboard is? You go to www.cmu.edu/Blackboard, and if you're registered in the course, you will have access to that, and you can download the chapters. The book is still in process, so please don't distribute the chapters. And some of the chapters are in better shape than other chapters. Sometimes there'll be things that are not from the book, and we'll post notes or papers and so on as needed. Everything will be on Blackboard. If you are an auditor, you should officially register as an auditor. I think that will give you access to Blackboard. If you're from Pitt or somewhere else, I think you still should get access to Blackboard. If you have any trouble, let us know, and we can make sure we give you access. Okay, so everybody in the course should be able to access the Blackboard for the course. All right, so let's see. So this is going to go into, what this course does is go into a lot more theoretical detail about the kind of stuff that you learned in 701. And there'll be things like we're going to start with concentration of measure, which we touched on in 705, but we didn't really do any proofs. Here we're going to actually get into the details and into the proofs. So the things we assume you're familiar with, therefore, is something like what's convergence and probability or convergence and distribution, what's the central limit theorem or the law of large numbers, what's maximum likelihood, what's Bayesian inference. These basic things, bias and variance, we'll assume already that you're familiar with those basic things. All right. You'll see that the syllabus has a list of other texts you might want to look at. The course will be based on 6 assignments. which will be handed in Fridays at 3 o'clock, and that'll be on the website when they're due. Mixture of theory and methodology. There'll be one exam, a midterm exam, Wednesday, March 6th. And there's a final project. So the project we want to be a little bit different this year. In previous years, the 702 project has been kind of like another 701 project. We thought, well, what's the point of that? You've already done a project like that. So the idea is to make this one, since this is supposed to be a theory course, is to make it a little bit more theoretical. And the idea basically is you'll kind of write a review paper about an area, a brief paper, 8 pages, like an EPS paper. But you'll pick an area, like let's suppose you're interested in, I don't know, support vector machines or Gaussian process regression. You'll pick an area, find the key papers, read about them, and write a very short paper which summarizes the main background, summarizes the main results, and even has some proof outlines of some of the key results. And so, the idea is that you won't be able to just take a proof from some paper and reproduce it, because that will take up the whole 8 pages. You'll have to think about the proof and come up with some sort of summary proof. And the idea is just to show that you've kind of learned in depth about one particular area. And that'll be what the project consists of. So there'll be various milestones throughout the course that are marked on the syllabus and on the webpage. There'll be a proposal due February 15th. That's just going to be like basically what you're going to work on. You can do these, by the way, by yourself or in teams of 2. Then there'll be a progress report at the end of March, and then the final report's due in May. The last class or 2 will be devoted to what are called spotlights, where you each get 2 minutes to present your whole paper. It's a lot of fun. And it's a good thing to get used to doing because you do these at conferences. All right. Now, is there anything I'm forgetting, Aarthi, that I should be saying?
No, but I just want to make 2 remarks. One is about the auditing. Make sure that you fill out an audit form if you're auditing it, because usually people forget to do that, and at the end of the semester, then there's an issue about whether you get, how much grades you get for it. If you are auditing and didn't do any homework, so you are forced to assign you a fail. So if you're auditing, do make sure that you fill out that form, get it signed by one of us, and submit it to her. That's one thing. And regarding the project, I think you're also open to, if you want to do some new theory or prove something, as long as it's not too ambitious. So if you're planning to do that and not a review, then definitely talk to one of the instructors. Yeah.
All right. Any questions about anything before we start the material? All right, this is a big room. So the first topic is concentration of measure. Now most of you probably didn't print out the chapter yet, I would imagine. Some of you might have. Some of you have computers with you and you can look it up. But don't worry. For today, I promise I'll write slowly and neatly. So, plus we're taping this. So don't worry too much about missing stuff. It's all in the chapter. Well, if it's not in the chapter, I'll tell you. There are a few things that are outside the chapter. It always makes it more interesting if we add a little bit of extra stuff. So I'll try to write large and neat here, but just let me know if you can't see something. So the first topic is concentration of measure. And concentration of measure is one of these tools that gets used all over the place whenever you do theory for machine learning. And so we want to start the course with that because we're going to be using it all over the place. We did touch on it in 705. What was the key theorem in 705 when we talked about concentration of measure? Hoofding's, right? So we're going to dig into that stuff a bit deeper. So what I'm going to start is with a bit of a review, even a quick review outline of the proof of Hoofding's lemma, and then we'll go into it a little bit deeper. So what are we talking about when we talk about concentration of measure? Well, we've got some random variables, z1 to zn, and we're interested in some function of those random variables. So let's say f. For example, the average, or something related to classification error, or some other familiar quantity. And this thing has a mean, let's say mu, and the goal is to say that the random quantity is close to its mean with high probability. So remember, we made statements like the probability of this difference is bigger than epsilon is small. small here means we want something little o of 1, something that's going to 0 as the sample size increases. The extra element that we refer to a little bit in 7 and 5, and that we'll go into much more detail here, is that it's not often, or rather it's very often that we are interested in not just one function, but a set of functions. So we might want to look at the maximum deviation. And so we need not just bounds like this, but we need uniform bounds. So yes, if you remember Hoeffding's inequality, it looks something like the probability that C bar minus mu, let's say something between 0 and 1, looks something like that. So that's the basic example to have in mind. Let me just remind you before we go, I'm going to actually just remind you the details of this for a few minutes. But before we do that, let's remind ourselves why we care about concentration measure. We use it in density estimation, we use it in regression, we use it in clustering, but we use it especially in classification. Remember, the typical example is you have Zi is actually a pair. And as usual, you want to predict Yi from Xi. Yi is binary. And the two quantities that are very interesting are, let's say, if I have a classifier H, so H maps X into 0, 1. Then what we're interested in typically, right, is the risk, the probability that you misclassify. We don't know that, so we use the empirical risk, or the training error, which is just counting the number of mistakes. So the quantity on the left is what we're interested in, the quantity on the right is what we observe. And the place we used Hoeffding's inequality the most was to try to bound the difference between this and this. How good an estimator is the empirical risk of the true risk. So the kind of thing we proved, and that we'll prove actually in detail here, is that the estimated risk and the true risk are close. Probability that that's bigger than epsilon is small. When we prove it, we'll say what the delta n is. But again, we don't just want to do it for one classifier. Whenever we do classification, we try to choose the best classifier among a set of classifiers. So we're actually looking at the maximum error over a set of classifiers. So this is the typical example of where we want to get this uniform concentration of measure. And let me remind you of one other thing, which is once we've accomplished this, then we can say on an event with probability at least 1 minus delta, the estimated risk and the true risk are close. And hence, on that event, so with probability, once we prove that, we know that with probability at least 1 minus delta, we get the following set of inequalities. We know that the risk of the best classifier, so H star here, minimizes the risk, true risk. Oh, sorry. This is a typo. I want the risk, let me try that again. The risk, what do we know? We know the risk, the true risk of the classifier that minimized the training error. To minimize the training error, that gives us a classifier. What is its true risk? We'd like to say that the true risk hopefully is not too large. Well, we know that on this event, small probability, that R and R hat are close, so that's less than or equal to R hat to H hat plus epsilon, because they differ by at most epsilon over all H's, so that includes even this randomly selected H. And of course, h hat minimizes this, so that's less than or equal to r hat of h star. And finally, we can replace r hat with r again at the expense of another epsilon. And so what that shows is with high probability, the risk of the selected classifier is pretty close to the risk of the best classifier up to this point. So that's an example of why we're interested in proving these concentration measures. So let's revisit Hoeffding's inequality in a little bit of detail, since that's going to be the kind of the basis for all the other stuff we do. I'm not going to reprove everything because a lot of it we proved in 705, but let me remind you of a key fact. If you have a random variable x trapped between two numbers, one of the things we saw in 705 is that gives you lots of information about its moment generating function. And if you have a bounded random variable, the expected value of this quantity, that's the moment generating function, we prove that this was less than remember that proof? That was something we used the convexity of E and we did a little bit of calculus. If you forget, well, you got those 705 notes, just go back and remind yourselves. It wasn't a very difficult proof. But the important thing is, once I tell you random variable is bounded, I have a bound on its moment generator. All right, so let's therefore remind ourselves of the proof outline for Hoeffding's inequality, which is pretty simple, which looks like this. Remember, we have the Hoeffding's inequality. Can you read the board back there? Am I writing big enough? So Hoeffding's inequality works like this. We have IID random variables, z1 to zn, again bounded with, say, common mean mu. And then we form the empirical average Hoeffding's inequality tells us that the probability that z bar minus mu is bigger than epsilon is less than 2e to the minus 2n epsilon squared over b minus x squared. That's what we want. We want the probability to go to 0 exponentially quickly. That's the most useful kind of inequality. So let's, if we just don't go in every detail, we can actually go through the proof in a minute. So let's do that. Just in case you've forgotten. I know it's unlikely. I think I won't be using that top word. Moment of weakness was caught on tape, too. I wouldn't have felt bad if there was like a really important theorem here. Somehow that would have seemed good to make it hard to move around. All right, so let's prove this. So without loss of generality, let's do this case with mu equals 0. You can always add and subtract mu. So we'll take mu equals to 0, and we'll do 1/2 of the inequality. It's a statement about an absolute value, but if you prove it in both directions, that's where the 2 comes from. So let's just do 1/2 of the inequality. And so remember, it goes like this. The probability that z bar is bigger than epsilon, that's the probability of the sum of z Z's is bigger than n epsilon. Now we do the so-called turn-off trick. Is that rather than trying to make a probability statement directly about the random variables, it helps to do a transformation of both sides so that we can exploit the information that this has a well-behaved moment generating function. So what we do is we take e to both sides and we put in an arbitrary positive number t. So this is equal to the probability that e and t to I is bigger than e. So that's the Chernoff trick. Now we hit it with Markov's inequality. The probability that this is bigger than this is less than or equal to the mean of this divided by this. So by Markov, that's less than or equal to e to the t, let's say I. Notice that it's the expected value of e to t to the sum, but e to the sum is the product of the e's, and because I'm assuming independence and I on b, taking the product is the same as taking one of them to the power n. And now we use this critical fact. I can substitute this in here. Well, mu is 0, so it's just this piece. So this is this is e to the t squared. And then the last step was, since this was true for an arbitrary t, that t was introduced. It's a variational parameter. It allows us to get actually a set of inequalities because each t gives us a valid inequality here, but we choose the best one. We minimize this over t. So minimizing over t gives you a stated result. So I hope that's now back to being fresh in your memories. The key tricks are, again, to not work directly with random variables, but use the Chernoff trick of raising it to a power and introducing a free parameter t. And then we can bring in the moment generating function, and we can optimize over the variational parameter. If we set the right-hand side of Hooking's inequality to some number, let's say delta, so make this probability delta and solve for epsilon, then we can restate Hooking's inequality by saying that with probability at least 1 minus delta, we get that z bar minus mu is less than or equal to the following quantity. Which is order. That's another way to think about what things inequality. High probability, z bar minus mu is about 1 over root n away. All right, so that's old stuff. Now we want to talk about a few extensions. Let me just see, though, are there any questions about Hooking's inequality now that we've reviewed it? Everybody's remembering it and everything? Good. You never know what happens over the Christmas break. You lose a few brain cells. All right, so let's talk about two generalizations of this, which is McDermott's inequality and Bernstein's inequality. And then I'll show you examples of each of those inequalities in a statistics problem where you can see that they're useful, whereas Hooking's inequality wouldn't be useful. So McDermott's inequality, or the bounded difference inequality, is actually a generalization of Hooking's inequality, which the generalization is to go away from sums. Instead of dealing with sums and averages, it deals with more general functions. Bernstein's inequality is a different type of generalization where it tries to give a more precise bound on the right-hand side of the inequality. So let's start with McDermott's inequality, or the bounded difference inequality. And as soon as we do the proof, I'll do an example and you'll see how powerful this inequality is. So the idea is, I have some function of z1 to zn. Now it's no longer going to be a sum or an average necessarily. Some arbitrary function, but it's got to be somewhat smooth. In particular, the key property here is that if I wiggle around one of the observations, we don't want y to change too much. So the way that's usually written is if we look at the function z1, zi, zn, so what I'm doing is I'm taking the function, evaluated at some arbitrary string. Now I'm taking the same function, but I've changed, this is, I hope you can see this, z prime. I've changed one point. And now I ask, what's the biggest I can make this as I vary I, as I vary z1 to zn? So this is the maximum change over all vectors z. And let's say that's some bounded quantity ci. So this is for all possible values of z. Okay, so wiggling one element of the function, of the argument of the function, only changes it by some fixed finite amount of ci. So you can see, for example, if f was the average, then basically that's saying when you wiggle one observation, how much is the average? It's like 1 over n, or only 1 over n, a small amount. And here's what McDermott's inequality says. So this, let's let mu again be the mean of this random quantity. McDermott's inequality says that we have something very similar to Hooking's inequality. In fact, Hooking's inequality is really a special case of this. Namely that the probability that the random quantity minus its mean is less than or equal to 2. So it's just 2 epsilon squared, and that's the sum of the ci squared. So just to do a sanity check, let's think about averages. So again, if this was the average of these, ci would be something like 1 over n, or maybe a constant over n. So what you'd have here is 1 over n squared, but there's n of them. So you'd have a 1 over n, which comes up here, and you get back exactly Hooking's inequality. So it really is generalizing Hooking's inequality. So let's look at the proof of this. A few steps, I'll just tell you, and you can, there'll probably be homework problems. Okay, so one step is somewhere on this board was our, which I've lost now, was our key fact, oh there it is, the top left there, that when x had a bounded random variable, that its moment generating function had that exponential form. Well, the same is true if x, we're talking about the random variable x conditional on some other variable. That's not too surprising. So I'm just going to state that if we have, suppose we have a random variable v trapped not between two numbers, but let's say between, let's call it some function of a random variable h of w and h of w plus c. So w is some other random variable. This is just now a generalization of the one in the top upper corner. Up there, A and B are constants. Here they're just random. They're functions of some random variable, and the difference between them is C. Think of that as B minus A. And that the expected value of B, given that random variable, is 0. Then, using pretty much the same proof, you can show that the expected value of B e to the TD, that is the moment generating function, given W, again, satisfies that same inequality. So if you just think of W as being constant here, you get back exactly that thing. So actually, here's a good one. We'll put that on. I hope it looks very plausible given what we already know about the case we used in hoping to. Okay, so now using that, we're going to prove McDermott's inequality, and it follows the proof of Hoofing pretty closely. There's a very clever trick. It'd be easier if you just. Well, actually, I should preserve this for it. Let's do this. So the tricky thing is, we're dealing with kind of an arbitrary function of the z's. How are we going to say anything about it? After all, it's not an average or anything. Well, the trick is to create a sum, even though we didn't start with a sum. And we do it as follows. Let's look at the quantity of interest, y minus mu. Let's call that v. This is the thing we want to bound. And the trick is, can we rewrite this somehow as a sum of random variables? Because if we had a sum, then we can use techniques similar to what we used in the proof of Hoofing's inequality. So actually, I'm claiming this is equal to a sum. It's the following quantity. Vi is the mean of y based on the first I observations minus the first I minus 1. So let's think about it this way. I put the data in order. Pretend they're coming in some time order. The order actually doesn't matter here, but let's just say, think of them as being in order. We're interested in the mean of this function of all the data. You don't know f of z, z1 to zn until you've seen all the data. But again, pretend I'm showing you them one at a time. And you have a distribution. In principle, you can compute the mean of that given what you've seen so far. And you can keep updating it as you see more and more information. So this is just the mean after having seen I observations, and the mean just before that when you saw I minus 1. And by the rule of the iterated expectation, if you think about it, this has mean 0. Just like, let me make an analogy. Well, actually, let's look at the mean y given z1 minus the mean of y given nothing. That would be the first increment. If I now ask you, what's the mean of this quantity? It's 0, right? Because this is already the mean of y. And when I apply the expectation operator here, it's the rule of iterated expectation, you get back just the mean of y, and it's 0. And if you just apply that one step at a time, you'll see each of these VI's has conditional expectation 0. So what I'm saying is that this random variable zi that's not clear, sit down and think about it. It's only a one-line proof. It's just a matter of applying the law of the iterated expectation. Just think of the z1 to zi1 minus 1 as fixed. And then take the expected value. So what have we done is just by taking this sequential expected values, we've written the quantity of interest y y minus mu as a sum of these increments. Sometimes this is getting into what are called martingales, where people think about gambling over time, and at any given time, you're expected, if it's a fair game, you're expected increment in wealth should be 0. You should expect it to be, they either go up, go down, but on average it would be 0. And you end up with these sequential gaps like this. All right, so all we've done then is, by definition, we've written this way. How do I know, though, that this reduces to this? It's a telescoping sum, right? If you look at the sum, I keep adding and subtracting the same quantities. The only thing that's left over after the sum is the original thing and the first thing, which is the last thing and the first thing. So I did that. That's trivial. This is just adding and subtracting. It's a telescoping sum. Okay, so now the rest is just a little bit of manipulation. So let's define one of these guys in here, let's say, hi of z1 to zi to be so in other words, I'm just giving a name. This guy here, I'm giving a name to it. It's a function of z1 to zi, and we're calling that function hi. Let's be clear about why is it a function of z1 to zi. Because remember, a conditional expectation is actually a function, a random variable, right? Just think about regression. When you look at the expected value of y given x, that's a function of x, right? That's saying this is what my mean of y would be if I observed a particular value of x. But until you've observed x, that's a random variable. It's a function of x, in other words. It's the same thing here. This thing is a function of z1 up to zi, so we're calling that hi. It has some distribution. Let's just call that fi. And so, in fact, the reason why I define that is because in vi, to be a little bit more explicit about it, is actually just this h thing. Vi is what we just defined, minus this one, which is less one random variable. It's just integrating out one of the random variables in h. Okay, so I haven't changed the definition, I'm just rewriting. I'm just saying call this first thing h, and then the second thing you can see, we're conditioning on one less thing. So I'm just integrating that. The reason for doing this is this allows us to say, look, how much can this change? I can now ask, think about this as some function, and say, how much can this function change as I flip one of the random variables? So, to put it another way, let's see, how is this? We can now say the following is true. Again, focus on time I. So suppose we're doing this, I was 1, 2, 3, we're at a particular time I. We're focusing on vi. So, what can we say? I'm going to define function in our generalized version of that inequality, which I will rewrite because did we lose it? Let me put that inequality up again. What was the inequality I referred to? I said that if this is true, if B is trapped between two things that differ by a constant C, where this has mean 0 in W, then again we have that moment generating function back. And And now I'm in a position to do that for the quantity VI, which is what we're interested in. Because from here, just try to make this as large and as small as possible. So in other words, I'm taking W to be Z1. So think of that as fixed. We've seen those so far. We're thinking about VI. The randomness is now in ZI. And we are in exactly this situation. Where this is CI, and what is H? H I'm defining to be the smallest I can make this function. I'm taking the current variable to be the thing we're going to minimize over and maximize over. All I'm saying is this function evaluated at zi, if I put zi in here, is precisely vi. And we're going to say how much can that vary? We just maximize and minimize this, and you can check, I'll leave this step out, that because of the bounded difference assumption, this whole thing can only change by at most zi. So that tells us that the expected value of e to the t vi given w is less than. Okay, so just to make sure I haven't lost anybody, let's just say all we've done is taken an arbitrary function, we've rewritten it as the sum of these increments. These increments have mean 0, and they're bounded. The changes are bounded. That's all we're doing. And that the boundedness, as I wiggle something around, says that the expected value of vi, its momentary function, satisfies that Hoofding-like bound. The last step now is, can we actually work through the steps of Hoofding's inequality? Almost, okay? Because these things aren't independent, these vi's, right? There's a lot of dependence going on here. So the trick now is to kind of peel off the observations one by one. So the last step in the proof is to try to mimic, we're going to try to mimic the proof of Hoofding's inequality. We're going to use the Chernoff trick, but we're going to kind of peel off one observation at a time. So all we do is the following thing. We say, here we go, here's the heart of the proof. The probability that y minus mu is bigger than epsilon. Well, first of all, we define these so that that's the sum of the vi's. Okay. And again, we Chernoff-ize it. So we're going to take the probability. So that part's all the same. We Markov's inequality. So we get so far, so good. Everything looks just like the proof of Hoofding's inequality, except we have to kind of find a way to deal with these VI's which have been defined in this incremental way. So here we use, again, the law of total probability, or the law of iterated conditioning, which is expected value can always be written as the conditional expected value followed by another expected value. And what we're going to condition on is the first n minus 1 observation. So I'm just going to rewrite this expected value as the expected value of a conditional expected value. Namely, the expected value e to the T1. And I'm putting this stuff up front. So let's pause, look at these things. I'm writing this one expected value again as two expected values. Expected value conditional on n-1, and the expected value over the remaining observation. But when I condition on z1 to zn-1, you can think of those as fixed. It's like z1 to zn-1 are constants. So that part of the sum I can bring out in front of that expectation. These depend on the things I'm conditioning on, so they're like constants. However, the nth one is still random, so it's still there. Does that make sense? And now, what we do is we use the fact that we have this bound on that guy. Star. So if it's star, using star, we have e to the epsilon, e to the t squared, cn squared over 8, and then we're still left with all the other stuff. So what's happened is, instead of doing that kind of hooking trick through all the observations, I peeled off one observation. All I did is condition on everything except the nth one. I used the moment generating bound and pulled that one out, but I'm still left with the other ones. But now you can see I can iterate it. Right now I can do n-1, n-2. So we keep iterating, and eventually we get e to the t epsilon, e to the t sum of the ci squared over 8. And we're almost done. We just have to optimize over t, minimize this over t. Whoops, I lost a minus sign here somewhere. Yeah. Here. This should be e to the minus. Minimize over t. And you get the stated result, which, let me make sure I state it right, is e to the minus epsilon squared. There's a 2 in the stated result because remember I only proved that it was bigger than, you have to do the other side of the absolute value. And you get 2. So if you've never seen this proof before, there's a few little tricky steps there, so it's worth reviewing that proof. Let me see, what time does this class go to? We go to 2:50? Right. Because we want to do now a few examples. Let's do 2 examples to see why this is useful. So example 1. If I have n observations from some distribution P, so we'll follow the same convention here that we had at 705, which is, unless stated otherwise, we always assume we're dealing with an IID sample, independent and identically distributed, and that means it's drawn from P. If we deviate from that, we'll say something. And we can define, remember, the empirical distribution, which is Pn of A. That's just the indicator function, 1 or 0. And of course, this is just counting what proportion of points fell into the set A. And one of the things we're interested in is how far is Pn from P. But we're going to look instead at a related quantity. I'm going to define G to be the soup So we take some class of sets, script A. Maybe the set of all spheres, the set of all rectangles, set of all intervals, whatever. For each one of those, I can compute the proportion of points in there and the true probability and take the maximum. This is the quantity we're interested in. This is some complicated nonlinear function of z1 to zn. So if I want to make a statement about this quantity, Clifton's inequality isn't going to help us. Notice I haven't said anything about what the class of sets is. What can I say using McDermott's inequality? Well, what's the most that this entire quantity can change if I move one observation around? Regardless of how complicated the class of sets is. Because the only place the data come in are here, and either you've changed whether an observation is in a set or not. So this either becomes a 1 over n or a 0. That's the only change. So we immediately get from McDermott's inequality that the probability that this quantity, so g, minus its mean, is bigger than, say, epsilon is that. Because C, I just put in the CI equal to 1 over. That's pretty amazing when you think about it, because it's a pretty complicated expression. Now, if you remember when we talked about a little bit about DC theory, which on Wednesday Aarthi is going to talk about, I guess, in great detail, this should set off an alarm bell, because in order to make statements about classes of sets, didn't we need to have some sort of statement about how complex the class, script A was and everything? And yet somehow now I seem to have thrown that away. Well, because it's not a complete statement. All I'm saying is that this random quantity is with very high probability close to its mean. What we haven't said is, what is that mean? What is the expected value of this deviation? That's where all the VC theory comes. So if you can use, say, VC theory or something else to show that the expected value of this quantity is small, that's part one. But then you want to say the actual random quantity is close to its expected value. That's where you can use McDermott's inequality. Let me show you another example of that, which is a little bit more interesting, which is density estimation. Now, density estimation, I'm kind of jumping ahead of it because that's a topic that's later in the course. I'm having a senior moment, and I'm forgetting that we even talked about density estimation in 705. I think we did briefly, right? Yeah. So we're going to talk about it, the theoretical details. Yeah, we did talk about it in 705, and I said, well, all the complicated theory we'll do in 702. We won't disappoint you, we will. But that's later in the course. Right now, I just want to use it as an example of McDermott's inequality, is when we have x1 to xn on a distribution P, and P has a density P. So you recall then that we want to estimate the density P sometimes for clustering or for classification, for various purposes. One of the estimators, and I think pretty much the only one we did in 705, is the kernel density estimator, which looks like this. Here, I should say, the xi's are in R to the d. So you get n random vectors, and remember you have to choose a kernel, which you can think of if you want as a little normal bubble, and a bandwidth h, which determines the amount of smoothing. So we'll go into all those details again later in the course, but just remember that you get some data, and from this formula, you get this nice smooth density estimator. And so later in the course, we want to talk about the properties of that in some detail. Right now, I just want to show you that, again, McDermott's inequality can already help us to say something about this quantity. In fact, I'm not going to talk about the density estimator itself, but rather the quantity of interest. Let's define G, x1 to xn, to be the following thing. I'm going to look at p hat of x. So what is this? This is a measure of loss. This is the L1 loss function. This is just some measure of how far p hat is from the true density. And again, a fairly complicated quantity. It involves an absolute value, an integral, this complicated sum, and so on. Nevertheless, we can still apply McDermott's inequality. Because, fortunately, if I change one observation, that function g cannot change too much. Why is that? Because if I think about evaluating this entire expression for some data set, and now again change one data point. So let's say xy1. Think about what that difference is. So what we're doing is in each case, we're looking at, let's call it p hat minus p minus, I'm going to call it p hat prime minus p. So this is the density estimator based on the original data, and this is based on just moving one observation by some arbitrary amount. But I can add and subtract p prime in here and do the triangle inequality. And what happens is all you're left with is the density estimator based on the original data minus the density estimator based on the data set with one observation change. Everything drops out. If I take two density estimators with the same data and subtract these, everything drops out. The only thing that's remaining is the ith one and the ith prime one. So this is less than or equal to 1 over n times 1 over h to the b I'm sorry, I got the, let me rewrite this. The integral should be here. And this might look like a mess, but it's not, because look what happens now. So all that's left over again is the I term and the I prime term. But if I do the triangle inequality, the integral of a minus b is less than or equal to the integral of a plus the integral of b. What's the integral of the kernel? In fact, with the bandwidth, what's the integral of the kernel? It's 1. The kernels integrate to 1. We choose them always to integrate to 1. So by the triangle inequality, this is less than or equal to this integral plus this integral, which is 1 plus 1. The whole thing is less than or equal to. So it looks complicated is the point. But when you start to write down what's going on, it's often the case that changing one observation, you can still bound it, even if it's a fairly complicated looking thing. So what that tells us, again, is that the probability that the loss function minus its expected value is bigger than epsilon 2 here. That's a surprisingly, again, powerful statement for something pretty complicated and nonlinear. The probability that this complicated random quantity minus its mean bigger than epsilon is tiny. Now that's not a complete analysis, again, for the same reason, which is we haven't said anything about this. This is where your bias and variance kind of calculations come in. So you can imagine doing this in 2 parts. You could do some sort of bias variance kind of calculation to bound the risk. But then if you want to actually know how far is this from the risk is the mean of this quantity. But if you want to know how far is the actual random quantity from this, McDermott gives you the answer. So it kind of breaks the work down into 2 steps. And later, of course, we'll talk about the risk properties of that in great detail. Okay, so I hope I gave you a flavor of where McDermott is useful is it's not a sum, but you can bound the effect of change in one observation. That's one type of extension of Hoeffling's inequality. Are there any questions? Okay, so that's a bit longer than I thought. Now I'd like to, at least we can start Bernstein's inequality. So as wonderful as Hoeffling's inequality is, we all love it. We use it all over the place. Now we've seen we can extend it to things beyond sums. However, sometimes it's not sharp enough. We often have to use a sharper inequality, that is something that gives us a smaller quantity on the right-hand side of the inequality. Well, the only way we're going to do that is somehow by using more information. And what Bernstein's inequality does is it uses information about the variance. If you have information about the variance of a random variable, you can do better than Hoeffling's inequality, especially when the variance is small. So this is often used in place of Hoeffling's inequality in certain problems, and in fact, you'll often get the wrong rates if you don't use this, you use Hoeffling's inequality instead. So, what is this? Well, when we did Hoeffling's inequality, we started by saying a bounded random variable has a nice moment generating function. We want to make the equivalent statement now, but also use the variance. We want to bring the variance into the expression somehow. So imagine we have a random variable, first of all. And by the way, there's a version of Bernstein's inequality that doesn't even assume the x's are bounded. It requires moment conditions. I'll just do the bounded version. So suppose the random variable is bounded without loss of generality, take the mean to be 0, and it has a variance, finite variance, sigma squared. Then what we want to do is use that information to get a sharper inequality. The first step is again to get a bound on the moment generating function. And this is the bound. It's a little bit more complicated looking. So it looks similar to the bound we had before, but there's more stuff going on here. And in particular, we see sigma squareds floating around. What we're going to do is we're going to do basically the same proof as Hoeffling's inequality. Basically exactly the same proof. But where we use the other moment generating function bound, we'll use this bound instead, and we'll see we'll get a slightly different bound. Let's actually, you might as well prove this because it's not too difficult. So you see where it comes from. So the proof works like this. Let's define quantity f, which is following infinite sum. So we're going to take the sum from r equals 2 to infinity of t to the r minus 2, the expected value of x to the r. We know that exists because we're dealing with a bounded random variable. You can see how you don't really need to assume that it's bounded. What matters actually is how those moments behave. But for us, we'll just do the bounded case. And so just to find this kind of strange looking quantity, why am I doing that? I'll show you why. Because it pops up very naturally in the moment generating function as follows. Here we go. The expected value of tx, that's the moment generating function. Probably you get a hint already from looking at the formula. This is what I'm about to do, which is I'm going to expand e. Right? The series expansion. So that's 1 plus tx plus the sum of the next terms, which are tr, xr, r factorial, so that's just the infinite expansion of e. Now, we want to have something involving t squared, sigma squared. So all that's happening actually is we're going to multiply and divide with t squared, sigma squared. That's going to reduce this r to r minus 2. And look what we have. Expected value of 1 is 1. Expected value of x is 0. And then we have t squared, sigma squared. And this, if I take the expected value, the only thing random is x. So when I take the expected value, I get the sum of the e in here, which is f. So the moment generating function is 1 plus 2 t squared times this sort of awkward expression, which itself, by the way, is less than or equal to this. Why? Because let me do another expansion. If I take e and expand this, I get 1 plus this plus a bunch of other stuff. So the right-hand side is equal to the left-hand side plus other stuff. So this is bigger than equal to this. So we're almost done here. The key is that this is less than or equal to, clearly it's just finagling this around to get what we want here, t squared and the sigma squared, and then there's some other stuff that we're going to have to bound. So the last step is to bound f. First of all, the annoying thing in f is all these expected values, expected value of x to the r. But I can always write x to the r as x to the r minus 2 times x squared, right? Remember that x is bounded above by c. So this is less than or equal to c r minus 2 times the expected value of x squared, which is sigma squared. So finally, we're almost done. All I have to do, I've bounded this by this, and I just want to now show you we can bound this and get the expression. And it's just a matter of replacing the expected values with these. So f, remember, is that sum t to the r minus 2. I'm now going to replace the expected value with this bound, c to the r minus 2. is replace the expected value with this. This cancels, this cancels. I'm going to pull out the t and the c to the minus 2. And what do we have? We have 2c. And the last thing to notice is that this is, again, just the expansion of e, but it's missing what? R equals 0 and R equals 1. So if I just take e to that and remove the first two terms, I get equality. So that's e to the 2c, and then minus 1 minus 2c. That's just moving the r equals to 0 and r equals 1. So that's kind of a dry lemma, not too exciting. The key message here is simply that we have a new bound on a moment-generating function, which appeared somewhere, which involves the sigma squared. And what we're going to do then, I guess at the beginning of the next class, is we'll just now redo. We're going to redo the proof of Hooking's inequality using this bound. And what we'll see, let me tell you what comes out of it, so at least there's some sense of accomplishment through sitting through that somewhat boring proof. Which is, we're going to say something to this effect, that the probability that x bar minus mu is bigger than epsilon. So that part looks like Hooking's inequality. I think I need a 2 there. I need a 2 here. So it looks just like Hooking's inequality, but notice there's this extra thing here. So for example, if sigma squared is really small, then this epsilon squared over epsilon starts to behave like epsilon, which is telling you that this deviation is much smaller. It's like order 1 over n instead of 1 over root n. Okay, so anyway, what we'll do next time then is we'll state this theorem, we'll prove it using that fact, and then again, if we have time, we'll do a couple of, I'm going to do the density estimation example, which is a good example of where you need to use Bernstein's inequality instead of Hooking's inequality. Okay, so we're off to a fairly technical start. But are there any questions? All right, so then we'll see you on Wednesday. Please download the first chapter and the syllabus.